Multiplicity of solutions. Let's consider an example, a PUMA robot. With this configuration, this robot reaches this point. If we use this other configuration, the robot reaches the same point. Now we can rotate the joint at the base and we can obtain this new configuration which also reaches the same point. With the same idea, we can also rotate this joint at the base using this configuration, and we will obtain this configuration which also reaches the same point. So in this case, if only position is considered, these four configurations set the end effector at the same point. This means that there exists a multiplicity of solutions. But what solution should we choose? Consider this example. I have this position, point A, PA, and I reach this configuration with these joints, QA. Now let's suppose that I want to move from this PA to this PB, and the joint configuration that reaches this PB is actually this Q2 or this Q1. So now for this PB we have Q1 or Q2. The question is, which one is better? Should we choose Q1 or Q2? If you see it graphically, it might seem to be better this Q2. Why? Because it's closer to QA, so the joints don't need to move too much. So maybe it's Q2. As I said, now we would need to evaluate the distance between the joint configurations. That is the distance between Q1, this new joint, and the one that we had already, and the distance between this other new joint, Q2, and the joint that we already had. And the shortest distance is the one that we will prefer. If we want to represent that mathematically, we can say that if there exist n possible configurations for PB, we have to choose the Q that minimizes this distance. That's to say the argmin of this distance for every single configuration that leads us to this point PB. Redundancy is something that is proper of robots that have more degrees of freedom than the number of degrees of freedom of the task. For example, consider this robot. In this case, this robot is only controlling the position of the end effector, no orientation, only position. Position has 3 degrees of freedom in space, but this robot has 1, 2, 3, 4 degrees of freedom. So position has only 3, but the robot has 4. So the robot is redundant with respect to this position because, as you can see in this picture, it can reach this point with this configuration, maybe with this other configuration, or even with this configuration. Actually, there exists an infinite number of configurations. This robot is redundant with respect to this position task. In general, let's consider a robot with n joints. Now let's consider that the task space is given by this representation. The important part here is that M is going to be the dimension of the task space. And you have to be careful here because, for example, if we deal with the orientation in quaternions, we would have 4 elements, but the dimension of that would still be 3, not 4. So it's important to say that M is not the number of elements that you have here, but it's rather the dimension of the task space associated with those elements. The robot, in this case, is redundant with respect to this task if the number of joints is greater than the number of, the dimension of the end of the task space. As an example, a 6-degree robot is redundant if the task is only position, if there's no orientation, because M would be 3. But the same robot is not redundant if we consider both position and orientation, because now M equals 6. And so we have 6 and 6, and this inequality does not hold anymore. For the complexity, equations in inverse kinematics are nonlinear. So there can be one solution, multiple solutions, infinite solutions when there is redundancy, or maybe no admissible solution if we are outside the workspace. When is the existence of a solution warranted for the position? When the position of the end effector belongs to the reachable workspace, that's to say to WS1. And when is the existence of a solution warranted for the pose, that's to say for the position and orientation? That is when the pose of the end effector belongs to the dexterous workspace, WS2. So we have some solution methods. We have analytic solution, which is exact and which can be preferred when it can be found because it's fast. The methods can be some geometric ad hoc approach, some algebraic also ad hoc approach, which consists in solving several polynomial equations. We can do some systematic reduction approach where we multiply things with other matrices and we take the inverse in both sides and we do sort of things like that. At the end, this is also algebraic. Or we can do some kinematic decoupling, which is called the Pieper decoupling for robots with 6 degrees of freedom. This can be done when the last 3 axes are revolute and they intersect each other. So in this case, we compute the inverse kinematics for the first 3 axes using only position, and then for the last 3 axes using only orientation. Another approach is numerical solution. They are iterative. In this case, this is needed when there is redundancy, because there are infinite solutions. It is easier to obtain because there's just a single pattern that you have to follow. It can be slower in runtime if you use a very old computer. In modern computers, it is not really very slow. Well, if you implement it correctly. If you implement it very naively, maybe it will be slow. Now, they also use the Jacobian matrix for the forward kinematics that we will see in a moment. And the methods that are used here are Newton or gradient descent, among others.